new trajectory, right? So you go over here, and then you decide, no, I'm actually going to go over there. So the question that we've been talking about a little bit is kind of smoothness and how do you restart a trajectory. And so the question I wanted to bring up briefly again is this idea of looking at the feedback channel. So let me do a slightly philosophical example. Let's say you got a simple robot and all you're looking at is height z. So I'm going to give you a graph of time versus z. And right now, you're at whatever height you're at. Well, fine, make it that. Right? Now, that's awesome. And if everything is good, that is both the commanded position and that's the actual position, because that's the ideal, right? But imagine I hang a heavy weight on here. What's going to happen? Things probably going to sag, right? So my point just being is that maybe your actual ends up being this being your desired, and maybe your actual is down here. So now if I give you a goal that is up here, you're going to create a new trajectory to go there. If you start the trajectory at the actual, what is going to happen to your system? If you think about it, it means that the command used to be this, and then you start at the actual and you do this as your command. Not surprisingly, would you agree that the actual is going to do this? Right? So this is the philosophical example of why I always argue you want to keep the desired smooth. The objective isn't to start at the actual, the objective is to keep the desired smooth, because if you keep the desired smooth, the actual will be smooth. Does that make sense? So, yes, we did use the feedback to initialize at the very beginning, but from then on, I actually believe that you should reinitialize at the last command, right? So always start at the last command. And the only reason at the very beginning we initialize from the actual, because there is no last command. So if there is no last command, you might as well go look at the actual and find out what it was, but otherwise use it. Does that make sense? Very related. Actually, I'm going to go over here. Some people play the game of saying, here's my goal, and now I'm going to send a command. Here's my heavy, and look at the feedback. Well, if I actually look at this, if I tell you where the goal is, and I see where I really am, what happens if I set my command to be my goal, let's say plus some constant, or maybe times goal minus feedback? Or if you say command velocity equals some constant times goal position minus feedback position. So if I do something like this, basically I'm saying keep moving until you reach your goal. Is that a reasonable thing to do? First glance, totally reasonable, right? The reason I bring this up is because if you implement this, you're going to have funny side effects. And the funny side effects are because if you say inside of the heady, what's really happening is you're setting the PWM, it is setting the PWM, equal to some position gain times the command position minus the, feedback position, right? And it actually has the minus kV times the command velocity minus the feedback velocity. It's doing that internally, right? That's what the heavy is doing. And there's like control modes, 1, 2, 3, and 4. I don't know if you remember that, right? There's different ways of setting that up. But it has gains internally, i.e. Kp, that it's doing. So if you implement something like these guys, then what you're really saying is this is command position, minus, the command position itself becomes this, right? It becomes goal position minus C times goal minus feedback, minus the KB part. And there's a KB in front of here. Sorry, this is plus. That was my sign notation. And if you look at that, that is nothing other than saying 1 plus KP, KP times 1 plus C, goal position minus feedback position. So I don't really care about the details of the math, but my argument is it internally is computing an error over the gain. If you do another error on top of it, really what happens is you're multiplying the gain. You're changing gains. So maybe it's good to change the gains. But my point is if you want to change the gains, right? Don't do it implicitly through a backhand. Just set the gains the way they are. Because in particular, that means that the system's behavior now is a combination of these two. If one of them changes, the other one has to change too. So now you've got interdependency between nodes, where parameters depend upon each other. Does that make sense? So in other words, adding the feedback in the command makes sense, but is really an indirect way of setting a gain. So I'm a strong advocate of not doing it, but just setting the gain in the first place. We haven't talked about gains. It's something that I want to get back to. Gains right now are set reasonably okay. When we have bigger and heavier robots, we may want to change the gains. And we'll do an exercise on that. As soon as we have a bigger motor, that'll be one of the exercises I want to do, is increase the gain so that you get good tracking for that motor. But the way I want to do it is actually go into heavy and do it. So all of what I'm saying with point 2 is use the feedback for initialization and not thereafter in the trajectory. I'm going to say something else in a moment. But does that make sense? Please. And this is just good design rules more than anything.
Yeah, I was wondering, did our implicit mover do that? Was that not what it did?
So did the implicit mover work off a fixed goal, or did you do one node and it was all meshed together? Or did you have an explicit, out of the detector I'm going to convert into a goal, and then I've got an implicit trajectory that converges the goal? So the way that I think of the implicit, where did I put that? Is to say command acceleration equals minus command velocity, and actually 1.4 is usually 1.4 lambda, minus lambda squared times command position minus goal, right? And then velocity is plus equals acceleration times dt, and position is plus equals velocity times dt. But it means that you are changing the command based on the goal in itself, but not the feedback, right? And so there's a loop. There's kind of a loop here, which is internal inside the heavy. So the heavy kind of has a feedback to command loop in here. This node has a loop in here. Does that make sense? So it's relevant to here. And so the heavy is in charge of tracking. If you bump into stuff, if you got a lot of friction, if the motor is overpowered, if you don't have enough voltage, right, that's the heavy's job. The trajectory generator's job is to get you a good command and to get you a nice smooth trajectory to that command, etc. And I'm kind of segmenting the two and saying the heavy is going to know about how heavy it is and what gain it needs, and the trajectory knows the time constant, right? And so lambda is 1 over t. So if you know that your new image is coming in at 2 hertz or 5 hertz, well, you probably want like a half second or something time constant to converge. That doesn't say what your gains are going to be in the heavy, right? So I'm separating those two. Hence, pseudo loops. Now, and the third point may come back to why you asked that question, but does that make sense? I still love looking at the feedback, right? And so, please, I do a detector here, right, that looks at those two and compares those two. So yes, I want to look at the feedback channel to see how well is it tracking. It's supposed to track really well. If it's not tracking really well, something's going on, so I put a detector there. So there's certainly reasons to use the feedback, but that's not a loop. That's just looking at it. And the other one, point 3, is kind of on the other side. So point 3 was looking at, if I have an XY coming in, I have a goal coming out, how do I do that? So let me double check. So if I have my silly little one link, because I don't want to draw much more, and I put a camera out here, right? Then basically this is my joint angle. But in the camera, I now see a face up here at this angle alpha, right? So do you agree that I really want to set a goal, in this simple case, to be Q plus alpha? Now, alpha, by the way, is going to be radians per pixel times the number of pixels. Right? And so you got to figure out what that is. And I think everyone kind of tweaked and played a little bit with that. But my question is, what is this? And I think that's where some of this comes in as well. Of the people that did 2 nodes, how did you do this? I know you guys did it. I don't know who else. I can't remember at the top of my head now.
Basically, we had the implicit control implemented. So we just keep on adding the position according to the velocity.
So you had 2 separate nodes.
Yeah.
So
That is not absolute.
So this was on the absolute side. This was on the detector side.
Yeah. So that gave alpha.
Sorry?
So that node gave alpha to our next node.
I absolutely just didn't understand it. I apologize.
It gave the alpha, he's saying. It gave us what
It gave us the alpha, but
yeah.
how did you decide on the goal?
So we figured out what the orientation of the motor should be, depending on where the face is.
Oh.
It didn't bunch of math.
So you gave it a relative goal, not an absolute goal.
Yeah. So
I guess there's that option too. I didn't even think of that one.
Yeah.
Okay.
So at every time step we just fed it, hey, where should you want to go the next time?
So you're giving it a goal relative to itself,
Yeah.
which is kind of just this piece. So bear with me then for a second, if I give it an absolute goal. So now the question is, what is it? So you can make it the previous command, right? Which is kind of like, you're supposed to be here, I see an alpha, well then you're supposed to be over there. So you could make this the command position. In some ways, that is easy because if you have it especially in 1, or if you're sending it, right, you've got the command position already in there. But if you think about it, this is actually a case where you want the feedback position, right? Because it's pointing here, that's where you took the image. And more than that, you actually want the feedback position at the time the image was taken. If I say that, do you agree with that? Because if I take an image and I'm 30 pixels to the right in that image, right, you actually want to know where was the arm when I took that image. Who had problems that the arms kind of oscillated and overshot when they converged? I think pretty much everyone did, right? I'm going to argue that's why. Because imagine this arm is moving, right? By the time that you actually process this picture and figure out what the alpha is, the arm is probably moved up here. So by the time you actually go to start your trajectory, you're effectively creating a target up there. right? Because this is the, I don't know, plus delta t effectively, right? This is the position that you've moved to in that time, right? And so if you think about it, if you're moving, by the time you get it, it's that your goal is going to be ahead. And if your goal is ahead, you're going to overshoot. And it's only once you come to a stop that you start realizing, oh, no, I actually need to head the other way. And then guess what you're going to do there? You're going to overshoot the other direction. And so you become a little bit oscillatory. And anyone that's done feedback systems, delays cause oscillation. Always the case. Please.
But if your commanded position is your previously commanded position plus the previously commanded velocity times your delta t, aren't you accounting for that? I mean, I get that there's going to be uncertainty, but
So,
if you have your delta t is fixed as like, oh, this is how often I'm sampling my computer sample.
it depends a lot on your detector, right? So if this is now, this is when the image was taken, right? And so it took a little while to run through my detector to get to here. So the question is, what's your movement, right? And so right now, you're here, and right now you've got a certain velocity, so you could argue that maybe I should have taken this point, right? So it's all a matter of how good is your approximation here, right? I mean, if you don't do any velocity, you're going to pretend that you took the image here. Does that make sense? So the short answer is, this is actually typical in anything that has to do with vision algorithms, right? The time that you take the picture versus the time that you finally get the information is always going to have some delay in it. And we're going to make that faster because we're going to go to native Linux, yay! But there's always going to be some time. So there's actually a ROS message, a ROS function for this. Guess what? ROS has, you need to dig, but it's in there somewhere. It's a little bit subtle. It's not absolutely necessary, and especially if we get faster and the delay gets shorter, you probably won't notice it. But if this is my node, in comes my XY, right? So I'm going to put a little subscriber on here, which has some callback function that I run. And I'm going to put a publisher out here that is going to send out my goal position. What you can do is a function, and I'm going to draw a little FIFO. You can subscribe to feedback, and this is called a quote, quote, message filter. They called it filter because I guess that's a generic number. And there's a subcomponent called a cache. So you subscribe to it, but instead of creating a callback, you just say, just stick it in a FIFO. Whenever you get a new message, stick it in a FIFO. And you can say the length, right? And so if you said 100, that would be 1 second at 100 hertz. And then at some point, you can just say, what was the message at that time point? So you can literally ask, oh, given that I'm subscribing to this message in the FIFO, give me the message at that time. So guess what? Read the time that comes on your image, ask for the position message of that time, voila, get the position that you were at when the image was taken. I didn't bring it up before because in some sense, again, do you absolutely need it? But at least I want to point it out to people because this is the right way to really do it. And it has all the infrastructure there for you to do it. So you just pull the ROS time off the incoming header, everything should be timestamped, and say, give me the position message of that timestamp, and then look at the position of that. And that will be the cue that you should really take. Does that make sense? So subtleties, which is why I didn't want to bring them up before, but I don't think I'm doing my duty if I don't at least bring them up at all. Thoughts, questions? All said and done, clearly everything worked well. If people feel like it, one of the last problem in this is I want to get the Nooks running. Irene has still been having issues, sorry, I shouldn't say it like that, but we haven't gotten them fully set. Assuming we get them set by Wednesday, I'd love for people to start using them, which really means, it just means running your code on the Nook and doing it remotely. So I mean, there's a little bit of, oh yeah, you got to SSH in and play that game, but it shouldn't be that different. So if you want to play with it and stick something like that in, right, you should see all this oscillation stuff go away. But, gut?
Ja.
Jawohl, der Herr. Oh, gut, ja, oh ja. Sorry. Now I want a beer, dang. Totally stereotyping, but so true. So what I want to talk a little bit today, and I want to wrap it up on Wednesday, is talk about detectors. Meaning, I think we kind of have a handle on this and this. We're talking about kind of the subtleties. We're talking about the philosophy of we got states here, trajectories, we're interpolating through time, and I think we're getting comfortable with all that. This has been a black box. And I'm assuming that most everyone is going to replace that black box with something else. Right? And if you're doing, let's say, a round green ball of yay size, i.e. tennis ball, those are pretty easy to detect, right? If you've got something circular, if you've got something of a particular color. But in general, we probably want another detector. And detectors ultimately are also going to be contact and physical, but I mean, a lot of it will be optical. So I want to talk about it. I want to talk about it a little bit, how to use OpenCV. So who's played with OpenCV? I don't know how much folks have. Cool. So it does show up. I know a bunch of people have done the machine learning. So I mean, if you guys have cool detectors that you want to try out on here and got more data and other, please, right? This is a great class to try all that stuff. But I want to do this a little bit this week. As we get the mechanisms ready, we can play with that. We can get OpenCV so that once we actually start, we understand kind of that infrastructure as well. I'm going to ask folks to train, and I want to talk about all of that stuff. A little bit of a, I guess they call it Viola Jones, kind of a cascade detector. It's not easy to do. I mean, if anyone has done detectors, right, you need thousands of images and samples. Except we have one advantage, which is we're not looking out at the world. We're looking at a particular task. So who had false face detections because all the door handles were like, I mean, everyone had the door handles show up as faces, right? Guess what? Those doors were not in their training set. For us, we know what the background is going to be. We don't need to train for every possible background. We need to train for our background. And so in particular, if you have a chessboard or something, right, a workspace, you're going to put blocks down, and you've got a camera on a fixed location, there's not going to be that much variability in stuff. We can fix the background. We can fix the lighting, put a nice light up. So I trained a couple of detectors over the weekend because I wanted to play with it. I trained them in the morning when the sun was shining, and then I tried them on night when my lights were on. It didn't work so well anymore. Clearly the lighting changed the shadows and that changed things. But we're in a room where the lighting is probably pretty constant, right? And so we have a known object, known backgrounds, known lighting. So there's a chance that we might be able to, with 20, 30, 50 images, actually train a detector that does reasonably okay. So I thought it might be fun to at least understand what that domain is like and play with it. Whether or not we end up using it, at least we'll use OpenCV to do these kinds of things. So let me talk just 5 seconds about the code. I put the package, the stuff that I did over the weekend up on as an example. It's a little bit subtle in that you've got to link the OpenCV stuff in it. So the make file, if you guys notice there's always this CMake list that shows up. The CMake list is subtly different in that it says include OpenCV, right? And you have to depend upon the CV bridge package, which is how you convert them back and forth. And okay, so that's all set up. Otherwise, let me just point out that you will have a message coming in. So if the message shows up, right, that will call the callback. So the callback is going to basically be this long detector. If another message shows up, it gets put on the queue. And guess what? If another message shows up, it gets put on the queue again. So the simplest trick we can do here is set the queue size to 1. Because guess what? When this one shows up, that one goes away. It just keeps last. And I actually double checked this because the documentation, in some places it says one way or another way, but I actually double checked it. It is the latest that it saves. Which means if you just block the callback, once this guy frees up, this guy is going to call its callback, right? And voila, you just run the detector on the latest image that you have. So the only comment is do a subscriber with a queue size of 1, and then you can just run it from there. that's all I was going to say on code, and I didn't bring my laptop because it didn't seem silly. I mean, you guys have seen it's a publisher and a subscriber, and the only thing that happens inside the callback, you basically get the image, right? You run the detector, and if you want, you can publish the image with a nice little rectangle on the bow side. So I mean, there's nothing philosophically any different from it, other than now you're calling an OpenCV function. So I want just take a look at the example, and hopefully that makes sense. So then let me talk a tiny little bit. We'll start it, and given that I'm running later than I meant, we'll finish it on Wednesday, about detectors in general, and see if we can take a little bit of, for those folks that aren't as familiar, a little bit of the mystery out. So I think of detectors as different kinds. There are rule-based, template-based, which in some sense may be the easiest. By rule-based, if we actually do a red circle, right? I mean, guess what? That's very simplistic kind of template and rule-based. If we do contact detection, you're probably going to say something like, oh, if my torque jumps up and my velocity goes to 0, that probably means I bumped into something, right? So I mean, rule-based, template-based can be really, really powerful if you've got a very unique kind of situation. The one I want to talk about, feature-based, which means you look for all these features, and then what you need is a classifier that then tells you, based on all those features, is it a object or is it not an object? And I guess there's networks, there's convolutional neural networks, and kind of the whole deep learning as the most complex. And I don't know, I don't think this is the class to really go through the theory of all of that, because there's plenty of other classes and that'll take us 8 weeks, and I don't really know that stuff. So I want to talk a little bit about feature-based, right? The idea being that you take your image, you look for a feature, which means you get a certain number, and you look at the entire image and a set of features, so that the image becomes a vector of numbers. Right? That's what a feature detector is going to give you. And then hopefully, if you look at that vector in a huge dimensional thing, you're going to have some positives over here and some negatives over here. And you're going to learn that there's a line, and everything on this side of the line is your object, and everything on the other side of your line is not, right? So you develop a classifier that basically finds where all the positives are in this high-dimensional vector space. And so because it's so high-dimensional, you need a lot of images to actually make sense of it, which is why you have these gazillion, people want thousands and thousands of images to give you something where you can actually see the pattern. Philosophically, make sense? So I want to talk about, this seems to be, as much as I can judge this, Viola Jones, which is well, I guess it's Paul Viola, two folks. Was it Michael Jones? It is Michael Jones. And that was actually a paper at CVPR in 2001. But that's one of the algorithms that shows up in many places. MATLAB has support for it. And so when I'm going to ask you to do it, you might as well train it in MATLAB because they've got a nice GUI and it's easy. OpenCV has support for it, right? So you can run all this stuff. So you don't have to implement any of these algorithms. So it's one of the standard ones that works pretty well, and that people kind of as default. I think nowadays there's a lot more moving towards obviously learning in deep learning, but this is still a staple that I think gets used a lot, especially for face detection. Is that a yes or no? So people that know this stuff, you're just dancing. He's just dancing. I thought you're trying to send me signals. Maybe you're sending me different kinds of signals. Four pieces in that. Question one is, what are the features? And we use kind of hard features. We'll talk about integral images just briefly, as a way of calculating them. There is a training step, which is the killer step, which is an auto boost, an adaptive boost algorithm. And then there is a cascade classifier that actually does the runtime. So, and I'm annoyed, I didn't bring the object that I used. But let me talk a little bit about the features they do. So this is meant, or was originally designed for faces. But the features they use are called HAR. And if I draw something like this, does that make any sense? So I'm basically saying, take your image, take a little sub-window, take all the pixels on the left, and sum them up, take all the pixels on the right, and basically compute the sum of all the black pixels, of all the pixels, I guess, in black, minus the sum of all the pixels under the white. Right, so you have a black and a white area. So basically I'm saying multiply all these pixels by +1 and multiply all these pixels by -1. And I may have switched the order, haven't I? Okay, we'll make this -1 and this +1. And then sum over all of them. Right, and so you can take an image of arbitrary size, take a box of some width and some height, and calculate the sum of the pixels here +1 and sum of the pixels there is -1. Which this is really good at finding edges. Right? Because if you think about it, if everything above here is one color and everything below here is another color, and all it looks at is intensity. Sorry, I didn't say that. R is a grayscale. So it is black and white. Basically, if all of these guys are really bright and all of these guys are really dark, right, you get a very extreme recording one way or another. If they're all average pixels, then they're going to average to about 0. Does that make sense? So if this is random noise, because the area on both sides is the same, it's going to average to 0. If there's more on top or on bottom, it's either going to be a positive number or a negative number based on which direction. So that's a feature that is good at finding edges. It also uses a feature like that and a feature like that, which are quote, quote, line features, where basically you've got 3 zones. You've got a minus, I guess I call it plus, -1, +1, right? Where that feature gets used, and if there's a strip of things, it's really good at isolating kind of that strip. And then the 5th one it uses is a corner, meaning it does an area that looks like this. Right? And so if you've got corners. So it turns out I did 2 objects that work pretty well. One is I grabbed a remote control. Because the remote control ended up looking like black, black, white, white, right? It had a certain pattern to it that was very nice and distinctive like that. And guess what? The features really found that pretty nicely. And then I decided that the problem with the remote control is when you put it upside down, you can't see it anymore. So then I decided to make a circular object, and I wish I'd brought it, and I totally spaced and didn't bring it. What I did is I took a glass, well, I took a can actually, and put paper on the outside, and basically gave it a stripe pattern with some cross lines. And I made an object that had a funny grid to it, and it wasn't symmetric, it was kind of it would look like something like that, right? And I put that on the table. And the nice thing is, that kind of pattern really worked well with these kind of features and stood out from kind of random noise backgrounds. And so those features were really good at finding that. And I think that's one of the magics of feature detection is like what features are good. The algorithm was originally designed for faces. Turns out, apparently, besides the fact that I can't draw, you guys have probably figured that out by now, right? The face kind of looks like something like this, where the eyes are darker, and the nose bridge is actually pretty bright and throws shadows on both sides. And so if you look at a face, that's it. And so it turns out the features that they found was a feature, I'm going to try to draw next to it, that basically had, maybe I should draw it a little bigger. It was that feature, I believe, that had the forehead and the cheeks, so kind of this feature with the black across here. I guess maybe I should actually draw it in color. So that was one feature that reacted really strongly. The other one was a feature that was the two eyes with nothing in between. And then the last feature is a dark on both sides of the nose. Those three features were the ones that were like the dominant features that really caught faces, which is also why when you tilt your face, it kind of goes away. Did you guys notice that in the face detector? Right? As soon as you tilt it, it kind of loses it. That's why, because the features are all designed to be this rectangular shape, and when you turn, it kind of goes, doesn't find it. So that's, I don't know the order of how they decided all these things, but that's kind of what they originally proposed this algorithm to be good for, and it does obviously good. They ended up using, I think, 6,000 features to get the kind of detection levels that you want. So clearly we're not going to be at 6,000 features because we don't have anywhere near enough samples. But if we pick objects that have very unique kind of situations with very unique lighting, we might be able to find things. So then, basically, you go through the image, right, and you try here, you try here, you try here, you try in all these different locations, this window and this feature. And you try this as a 2x1, you try it as a 4x2, you try it as an 8x4, you try it, this is a 2x2, a 3x1, right? You try it in all the different sizes so that the features have different sizes. Which means you get like a couple 100,000 different possible features if you try all these combinations of different sizes in different locations. So, two things that they do. Here, I'm drawing this up a minute. How's our timing? I got 2 minutes. One is, and then we can finish it on Wednesday. They use integral images, which means they take an image, and if this is a pixel value of x and y, right, what they basically do is they sum so that at this point, this s of xy is the sum over all 1 through x, and the sum of all 1 through y of all the pixel values above it. Sorry, I, j. Does that make sense? And so the sum, or the integral image, is basically the sum of all the pixels to the top left. Which means if I want to find a rectangle, and I want to sum all the images in the rectangle, do you agree that I can just take the 4 corners and do the sum of all pixels in the area is A plus D minus B minus C? D is everything. Subtract B, it means you're subtracting everything that's in the top half, so you're left with this strip. Well, add A to it, you've got this piece. Subtract C from it, and it pulls that away, and it leaves you this guy. So if you compute, take an image, compute the integral image, which means you calculate everything once through that image, it means you can find all of these shapes really quickly. So calculating these becomes a lot faster. So one of the benefits of the algorithm is you can calculate these features actually really quickly. If you have features that are weirdly shaped, it's a lot harder to calculate thousands of them. The second thing that they do is the training. What they actually do is you take your training image and you literally calculate 100,000 features. And then you look at the classification, because you've got positive and negative, right? You've said this is the object in the image, so you know when it is an object and when it's not, right? So supervised learning, you tell it which are true things and which are false things. And so it figures out which features most dominantly correlate to yes and no. And so the training set, and I'll go through it a little bit more on Wednesday and we can wrap it up, basically finds you the minimum set of features and ultimately gives you a weighted sum. So that means step 3, HADA means that the final answer is going to be a weighted sum of alpha I times feature I, right? Where I is now going to be 1 through, I don't know, hundreds or thousands of the hundreds of thousands of possibilities. And that step is actually complicated in that it first finds a set that's good, then tries to find a set that matches well, and it kind of goes adaptively, and I'll go through it a little bit on Wednesday. I don't know that we need to go through the details, but I kind of want people to have some sense of what's going on. And so there's this training step. And that training step MATLAB does for you. So literally what I'm going to ask you to do is take 40 pictures of the object. Take 3 times that many without the object. Right? And if you're good, you can download them from ImageNet and do all kinds of stuff. But let's take one object, and then let's just basically put it down, take a picture, and then let's take 3 pictures of without the object. If we pick objects that are reasonable and keep the lighting somewhat consistent and that kind of stuff, there's a good chance that this training algorithm will actually come up with a decent feature set. And then there is an online cascade classifier which we can run. And so this guy spits out an XML file, and this guy reads the XML file, and voila, he knows all the parameters. And the only thing, and again, I'm rushing through here, what it does is it does it in stages. So stage 1, it looks at the entire image and looks for, are there, given the first 10 features, or actually maybe the first 1 feature, is there a candidate? And if the first feature already says no way, it throws it out. And so the cascading, and the reason it's called cascading is it scans through the image and finds possible options. In the second stage, it takes 10 features on those possible options and eliminates even more. Third stage, it takes 100 features, and I'm making up these numbers, right? They're not penned. But basically, it scans through the entire image with a really bad detector and finds just the very few options. And then it refines those options, and it refines, and it refines, and keeps going more. So that it doesn't actually ever calculate every feature on every possible thing. Anyways, tell you what, we'll spend 10-15 minutes and we'll go through that on Wednesday. But if nothing else, I want us to play a little bit with it, get some kind of feel for it, get the OpenCV up and running, so that'll get us the infrastructure to try other detectors. And if you guys want to try them this week, that's